For decades, the Indian military's ability to deploy advanced combat drones depended on foreign contractors. Relying on Western nations for high-tier unmanned aviation created a long-standing strategic vulnerability in their defense architecture. Modern unmanned combat requires platforms capable of penetrating contested airspace at near supersonic speeds, pulling maneuvers that would compromise the structural integrity of conventional airframes. To address this, the DRDO initiated a domestic program in 2009. The objective was the development of an entirely indigenous combat drone, establishing a 17-year timeline for research and testing. While designing a stealth airframe is difficult, building a domestic jet engine to power it is the primary barrier to aerospace independence. Without a reliable homegrown propulsion system, an indigenous drone remains a prototype rather than a weapon. That engineering impasse has reached a resolution. India's Defense Procurement Board has officially greenlit the acquisition of the DRDO Ghatak combat drone. This decision marks the point where two parallel, decades-long technology programs, the stealth airframe and the domestic jet turbine, have finally aligned for operational use. The first track of this convergence is the DRDO Ghatak itself. This demonstrator model highlights a flying wing geometry. The sharp leading edges are designed to scatter radar waves, while the air intake is positioned on the dorsal side to shield the internal turbine blades from ground-based detection. This silhouette illustrates the Ghatak's 12-ton weight class, matching several manned fighter aircraft. To move this mass, the design achieves a maximum velocity of Mach 0.9. The aircraft operates at a 13-kilometer ceiling with a 2-hour flight endurance. These capabilities were demonstrated in the real world during two critical flight tests, the first in 2022 and a subsequent flight in December 2023. While these tests proved the aerodynamic viability of the airframe, the program's success depended entirely on the second track, domestic propulsion. Track 2 centers on the propulsion system, the result of India's long-term effort to develop an indigenous jet engine. The propulsion system selected for this program is the Kaveri Dry Engine variant. Stealth drones often utilize non-afterburning engines to reduce their infrared signature, making them harder to track with thermal sensors. This physics vector shows the engine's core requirement. The Kaveri Dry variant generates between 49 and 52 kilonewtons of thrust. Reaching this massive output requires the internal turbine blades to withstand thousands of RPMs while exposed to superheated exhaust. Mastering the advanced metallurgy required for these extreme conditions is one of the most difficult challenges in aerospace engineering. A 50 kilonewton output provides the specific thrust-to-weight ratio needed to propel the 12-ton Ghatak airframe to its Mach 0.9 top speed. The pairing of this specific engine variant with this specific airframe represents the technological threshold required for a fully indigenous platform. The Defense Procurement Board has now moved past the testing phase, authorizing the acquisition of a 60-unit fleet of Ghatak drones. On a tactical map, 60 low observable signatures represent a significant increase in the capacity for synchronized, unmanned penetration of contested airspace. This order also establishes the first commercial use case for the Kaveri engine. Committing to a 60-unit fleet provides the domestic aerospace sector with the consistent funding and operational feedback needed to refine high-performance manufacturing. Achieving this massive scale of production requires the entire domestic supply chain to move from hand-built prototyping to high-precision automated assembly. The integration of the Kaveri engine with the Ghatak airframe marks the end of a 17-year engineering trial, demonstrating India's ability to design, test, and now mass-produce a high-performance domestic combat drone.